Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a senior researcher here at the SETI Institute, where I'm located at the moment. And today we are going to talk about the clues on the origin of life in our solar system by exploring the question of finding life in worlds in our solar system, especially on Titan and Europa. And to have this conversation, we invited two very interesting and well-known scientists that I've been the pleasure to meet and work with on some occasion. So first of all, Zibi. Hi, Zibi. How are you? Zibi Turtle. You can unmute yourself.
Hello.
Yeah.
Yes.
Hi.
Hello.
Okay. So Zibi is the principal investigator of the Dragonfly mission, which will land a drone-like vehicles on Titan. And we are going to talk about how this mission will search for life, collecting samples on the surface of this frigid satellite. And nearby me, we have Morgan Cable. Hi, Morgan.
Hello, Frank. So happy to be here.
Nice to see you and to meet you in person. Morgan is working at the Europa Clipper mission, and you're located at JPL, right?
That's correct. The NASA Jet Propulsion Lab in Pasadena.
In Pasadena, just only 700 kilometers south of here. She's going to talk about this Europa mission and and of course this very interesting satellite. So I remind our viewers that you can tell us where you are watching us from. And we will have a conversation for 20 minutes roughly, and then we'll take some questions from you. So get ready. But before taking questions, I really want you to give us an overview of what are Titan and Europa and what we know about those satellites. Zibi, let's start with you.
Sure, I can give a quick summary of Titan. Titan is the largest moon of Saturn. It's actually the second largest moon in the solar system, behind Jupiter's Ganymede. And so it's a little larger than our moon, the moon that we're used to seeing in our sky. Titan is really unique. It's a very unusual moon in that it has an atmosphere, and that atmosphere is actually denser than Earth's atmosphere. So it's actually the second densest atmosphere we have on a body with a solid surface in the solar system. And this atmosphere at Saturn is very cold. So the atmosphere is primarily nitrogen, but the next most common constituent is methane. And so there's all sorts of really interesting carbon-rich chemistry occurring in Titan's atmosphere and the surface, and we can talk about that more and what Dragonfly is going to do to study that chemistry at Titan.
Okay, and what about Europa, Morgan?
Oh, gosh. Well, all of these ocean worlds, these places that have liquid water oceans, are fascinating for different reasons, but Europa is certainly no exception. It may not be the biggest moon in the Jupiter system, but I'm a little biased. I think it's the most interesting, and that's because underneath that icy crust you can see behind me is a large liquid water ocean, about 2 to 3 times all of Earth's oceans combined. And evidence from missions that we've sent here in the past, like the Galileo mission, really indicate that this could be a very habitable ocean. That means that it may have all of the conditions for life as we know it to exist. So is it there? Well, the Europa Clipper mission, which is going to launch in 2024, will help us get a better idea of how habitable that environment might be. And if there are some bits of life or evidence of it on the surface, we may be able to detect that as well. So I'm happy to talk more about that.
Good. Yeah, so I'm a planetary astronomer, and some of you know my work is all about observing satellites of Jupiter, or any planetary system body using ground-based telescopes, which is great. I mean, we have sometimes some fantastic image using the 8, 10, 30 class telescopes, but it's still remote observation, right? And remote observation, one of the problems we have is that we don't have a good resolution on most of the images, good enough to see very thin structures on the surface and see the motion of them in some cases. And also we cannot analyze samples directly. So I'm very curious to hear more about those two missions. And we're going to start with you again, Zibi. Tell us a bit about Dragonfly.
Right. So Dragonfly is a rotorcraft lander. It's a New Frontiers mission, like Juno or New Horizons or Osiris Rex. So it's in that class of mission, and the plan is to send a rotorcraft to Titan. So Titan, because it has an atmosphere that's denser than Earth's, and because it has low gravity, the atmosphere is about 4 times as dense as Earth's atmosphere, and the gravity is about 1/7. So that means it's actually physically easier to fly on Titan than it is to fly on Earth, right? You could put wings on, and you'd need, something to breathe and a good sweater, but you'd be able to fly, over the surface of Titan. But before we get to send people there, we're going to send a robotic emissary in the form of Dragonfly. So very similar to the Mars rovers that drive across Mars, Dragonfly will fly from place to place, and this allows us to get to very different environments, traveling over, up to 180 kilometers, a little over 100 miles during the lifetime of the mission, which will be about 3 years. So we can make measurements in really different environments on Titan. And that's important because we know that there's all this carbon-rich material in Titan's atmosphere that has fallen out onto the surface. But we also know that Titan, as an icy satellite and an ocean world, there have been opportunities for this rich carbon, these large carbon molecules to have mixed with liquid water at the surface of Titan in the past, at sites of impact cratering, for example, where there'll be a lot of melting of the water ice crust, or possibly, via exchange with the internal ocean. So what we want to do with Titan is to understand how far organic synthesis really can have progressed in these environments that have, that are very different on the surface. And we could talk about Titan for a long time, but just very briefly, Titan has actually a very Earth-like environment. Even though the materials are very different, Titan is surprisingly Earth-like. So there are clouds of methane and methane rain and methane lakes and rivers and seas on the surface. And there are even sand dunes composed of these, organic sand grains. We don't actually know how those form. So, so there's just a lot of really fascinating chemistry, and this chemistry may be very similar to the kinds of chemistry that occurred on Earth before chemistry kind of took the leap to biology here on Earth. And so Dragonfly is really, fundamentally a prebiotic chemistry mission. We'll take samples of the surface, understand what those materials are and what processes may be at work, whether they're producing biologically relevant compounds. And just to kind of echo back to what Franck was saying about about remote sensing, Titan is actually because we have this fascinating weather systems on Titan. Earth-based telescopes are really great for tracking the weather and watching the clouds as the seasons change. It's hard to see down to the surface, but Hubble was actually the first telescope to give us images of Titan's surface from Earth and to show us some of the large-scale features. So there's still a lot that can be done with remote sensing at Titan too.
So tell us about Europa Clipper, Morgan. What's the missions going to be doing exactly on Europa?
Sure. And it's actually really funny that Zibi brought up Hubble right at the end there, because Hubble is also a reason that we have some tantalizing evidence we want to confirm at Europa as well. There is some evidence suggesting that there could be a plume of presumably liquid water that when it gets out into space, it freezes from some sort of subsurface reservoir at Europa. Now, this would be really exciting for us because we have past history with a previous mission, Cassini, that was able to fly through a similar plume at another ocean world, one that's present around Saturn called Enceladus. And in doing so, we were able to get some in situ measurements from orbit, from flyby. And Europa Clipper is definitely going to be able to do that too. Zibi, of course, is PI of one of the instruments on Clipper, and I work on Dragonfly, so we've got a lot of overlap. But some of the instruments will be able to get spectra, so light reflected off the surface, to tell us what that surface is made of. And then there are two instruments, you can kind of think of them as like sticking out your tongue and trying to catch a snowflake. But if your car was driving, 5 kilometers a second, so many times faster than a speeding bullet. Turns out that's just right, though, because if that snowflake hits a metal surface, it'll go poof, and you'll get all of these molecules that are trapped inside that ice grain now become ionized, and you can analyze them with special instruments called mass spectrometers. And so we'll be able to look for things that are sputtered off the surface from like micrometeoroid impacts and stuff like that, as well as if there's this plume, we'll be able to fly right through it and get an idea of what the gooey insides of Europa are like. And that's just a taste. There's all sorts of other instruments on board that I can talk about as well.
Good. Yeah, I would love to talk about all the instruments, but today we're going to talk about life specifically. We are the SETI Institute, and most people watching us right now, they're very interested in learning about how we're going to find life on other planets, and specifically in this case, on those exotic worlds. But before talking about this, I just want to mention that we have people watching us from everywhere in the world. So hello, thank you very much for watching us. We are talking about life, search for life in our solar system, specifically Titan and Europa. So we have people from Melbourne, Australia, Worcester, UK, Darmstadt, Germany, Louisiana, Delaware, Lagos, Nigeria, Sacramento, California, St. Lucie, Florida, Iowa, Latvia, England, Montreal, Shetland, UK, Budapest and Hungary, Nova Scotia, Canada, and South Carolina, Scotland, Ireland, Iraq, New Jersey, Essex. Wow, we have people from everywhere in the world. We have more than 100 people watching us at the moment, because there is truly an interest in learning how we are going to find soon life in our solar system with those future missions. So I'm going to ask a very naive question for both of you. We are not going to sample a piece of Titan or a piece of Europa and see microbes. Or if that's the case, please let me know. So how do we find life on planets like that? What's the chemistry, or what kind of instrument is being involved?
Right. So for Titan, as I said, for Dragonfly, really, we want to understand the chemistry that occurs that can lead up to biology. But we don't have reason to believe that biology does exist on Titan or has existed in the past. But we do have, because we have the ability to make very detailed chemical measurements of the surface materials on Titan. We also have the capability to identify chemical biosignatures if chemistry actually did take the leap to biology at some point in Titan's history. Titan is very cold, right? The surface temperature is 94 Kelvin. So life as we know it, water-based life, we would not expect to be terribly happy at the surface under current conditions. But at sites of impact cratering, where you get large warm pools of liquid water that can have existed for extended periods of time, we can't rule out the possibility that something happened there in terms of biological processes instead of chemical processes. We don't expect it. The other aspect of Titan, I mentioned the liquid methane in the system. So it's possible that liquid methane could also act as a solvent for biological systems. So maybe, there could be exotic, biological processes on Titan. We really don't have reason to expect either hydrocarbon or water-based life on Titan, but we cannot rule that out. And so, we would be remiss if we didn't ask the question and look for biosignatures if they are present. So Dragonfly has a mass spectrometer, and we'll take samples of the surface. There are 2 drills on Dragonfly, and we can break up the surface and use pneumatic transfer, just like a vacuum cleaner, to bring the material into a mass spectrometer inside the rotorcraft, inside the lander. And this will allow us to make detailed measurements of the chemical compositions and the structures of the molecules. And so in this way, we can look for possible signatures of biological control of the production of compounds as opposed to chemical, or abiotic control. Things like patterns in the mass distributions of the molecules, also the handedness of molecules, right? If molecules have the same composition but the mirrored structure, abiotic processes tend to just produce both. But biological processes tend to favor one over the other for simplicity. And so we can, by virtue of being able to measure the structure of the molecules, we can look for imbalances, in the chirality, the numbers of each of the different mirrored versions. So there are different signatures like that in the chemistry that can be indicative of biological processes at work. And so we'll be able to see if those are present, and if and if they are, then we'll have the challenge of interpreting that in the Titan environment. But if they aren't, we're still fundamentally trying to understand how complex the chemistry is on Titan. So from a Dragonfly perspective, it's kind of a win-win. Either way, we get really awesome chemistry, or if there is biology, obviously that would be really interesting as well.
And we will know that when. Roughly, just to give us an idea.
Right. Yeah, so Dragonfly is scheduled to launch in 2027, and will arrive at Titan by 2034. So we'll be exploring Titan in the mid-2030s. The mission duration is about 3.3 years. So we'll have a lot of time to explore different sites and travel from place to place to make these compositional measurements in environments that have very different geologic histories. So it'll be interesting to see how things vary across the surface as well.
Okay, Morgan, you want to do an overview of what will be the instrumentation on Europa Clipper and the future mission maybe to find life?
Sure, yeah. And I wanted to build off of a couple of the excellent points that Zibi made. One of them being that when we look for these chemical signatures of life, or other signatures, maybe if we see some structures that have been made, either micro or macro scale, that we try to be as agnostic as we can, right? Because right now, when you're doing astrobiology and you're looking for life, we have a sample size of one, right? We have one place where we know life exists, one essentially type of life, one example to draw from. But when we're exploring these places like Europa, like Titan, and beyond, we don't want that to bias us in terms of the kinds of biosignatures we look for, the types of molecules, or the type of morphologies we might search for. And so I think some of the techniques that Zibi highlighted are really excellent, because instead of looking, say, for only one molecule or only one kind of molecule, instead we are looking at patterns amongst a broad distribution of the things that could be there. And in each of these cases, we ask ourselves, okay, is what we see consistent with abiotic chemistry alone, so just chemistry happening without life there? Or is it different in a way where it looks like life might have had an influence? Life needs certain molecules in abundances that are different than if just thermodynamics and abiotic chemistry is at play. So these will be the same kinds of things that we do with Dragonfly in terms of those tests. We'll be applying to some of the instruments aboard Europa Clipper, as well as future missions. And the other really important thing is that we're not just going to do one test, right? So we've learned a bit in the past when we've tried to do some astrobiology missions that the more independent lines of evidence you have, that maybe they're looking for completely different things, or they're running a completely independent test, that's great, because then let's say that one of your life tests shows something interesting. Okay, that's kind of cool. But what if you have 3 or 4 or 5 or even more that all say something weird is going on? This is not abiotic chemistry. There could be life here. That's a much stronger case than if you just had one experiment. When it comes to Europa Clipper, the main goal of this mission is to understand the habitability of Europa. So we're not planning on landing yet. There are future concepts that are in work right now to do just that later on. So Clipper is going to assess the chemistry the geomorphology, the history, how Europa came to be. And in doing so, we're going to form a much more comprehensive picture of what Europa is like, such that now when we design a future lander, we will be able to even better tailor those instruments to be able to tease apart that life signal. Even if it's really, really faint, we should still be able to see it and not get confounded or confused by other inorganic molecules, for example, that could be present.
Okay. Well, we're going to take some questions from the audience, but before that, we have people who join us from other places like Croatia, Missouri, Oregon Coast, Netherlands and Pakistan, and Grand Prairie, Texas. I also would like to thank Crashalido for their Twitch subscription, and also Stafford for sending stars on Facebook. We are streaming on various platforms at the moment, so we have people who make donations or help us or just give us some visibility with those stars and those turn up. So anyway, I have some questions here from one viewer is asking, how come Titan has such a thick atmosphere? Do you have any explanation yet for this?
That is a very good. That's a very good question. Why Titan is unique in having an atmosphere, and another question is how long Titan has had an atmosphere. And so there's some aspects of that we'll be able to get at by making measurements with Dragonfly of atmospheric constituents to try to get at the history, the timeline, and the amount of resupply. One of the really key aspects of that is that the methane in Titan's atmosphere, the really complex chemistry in the atmosphere, is the result of the breakdown of methane at the top of the atmosphere. And as a result, the methane is destroyed. So that means that there's actually a fairly short lifetime for the atmosphere. The methane is destroyed on the order of maybe 10 million years. But the evidence of the geology on the surface of Titan suggests that the atmosphere has persisted for extensive periods of time. And there are a number of other lines of evidence that suggest that as well. So that indicates there must be some sort of resupply of methane to the atmosphere. There must be reservoirs somehow within Titan that can resupply the atmosphere, which is particularly interesting and suggests possibility of transport of material within the ice shell on Titan. And that's for all of these ocean worlds. That's one of the key questions we want to understand is what kind of transport there can be between the surface and the ocean. The same is true at Europa, where we have this fairly thin, comparatively ice shell, maybe 25 kilometers thick, which in the scheme of things isn't that thick. And so there's the possibility of transfer of material, like Morgan was talking about with respect to the plumes. So the atmosphere of Titan is one of the is something that we're still working to understand. It's a fascinating place.
In fact, you bring me to the next question. We had a question for you, Morgan. Can you tell us the last information we have on the size, the depth of this ocean? Are we now truly certain there is an ocean on Europa?
Well, when you ask a scientist to be certain about something, we can tell you that to a certain degree of confidence, right? And I would say that we have very strong evidence that there is a global subsurface ocean. Typically, the way that we do this for all of these ocean worlds is we send a spacecraft by, either to do flybys or orbits that has a fancy compass, a magnetometer. And basically, whenever we do these flybys, we may notice if that world has an induced magnetic field. That tells us that there has to be a conducting layer that can conduct essentially electricity, electrons deep inside. Now, that could either be molten rock, like on Earth, down deep, or it can be salty water. Well, how do you distinguish between those two? Well, we can also figure out the mass of these bodies as we orbit them. They pull on us, our spacecraft slightly pulls on them, and we can guesstimate what the mass is. And what we figured out is Europa is too light for that to be molten rock. So by process of elimination, it has to be a salty water ocean. And in terms of the depth and things like that, we have some constraints. As Zibi pointed out, that the ice shell we think is maybe as thin as 25 kilometers. Underneath that is where the ocean starts. And Zibi, I can't remember how many, if it's 100 kilometers-ish or something like that, the depth of the ocean.
Yeah, I think it's like 120, 100, yeah, it's somewhere in that range.
Yeah, that sounds about right. But that's one of the things that the Europa Clipper mission will be able to do to much greater fidelity than we have in the past. And that's important for us understanding things like the age of the ocean, some of those exchange processes that Zibi talked about between the ocean on the inside and the ice crust on the outside. That's important for us to understand. Europa's surface is really young. It's only about 50-ish million years old, which sounds old, but it's not, right? Like if T-Rex had his tiny little telescope and was like holding it up with his little hands, he would have been too old, he or she. You can have female T-Rexes too. But the point is, it's really young, right? Since the dinosaurs extinction happened. So this is very exciting for us because that means that if the surface is young, it could be pulling up or having recently exposed some material from that inner ocean. And if we're able to sample that, whether it's sputtered up, whether we fly through a plume and collect some of that material and look for organics and things like that, we can have a much better picture of what Europa's ocean is like and whether or not life could be there today.
All right. So we have now a lot of questions. So I'm going to ask you to answer very shortly to all those questions. So because I know you're extremely busy, you have probably an agenda which is crazy. One question for you, Morgan, is when Europa Clipper will arrive on Europa?
So
around Europa.
Launch is 2024, and I believe cruise is something like 3 years. Zibi can correct me if I'm wrong there, because it depends on which rocket we go on, and that was just determined.
Yeah, it's like 6.5, I think, with the current plan.
Yeah, space is big, right? And
space is big.
People don't always realize, like the distance from Jupiter to the sun, you have to do that again to get to Saturn. It's like big, space is big. So yeah, so launch in 2024. And so we'll get there in around 2030-ish, and then start our primary mission. So really exciting.
So Zibi,
and that's a 3.5 year. That's a 3.5 year mission with like 50 flybys of Europa, 40 to 50 flybys of Europa. So, so there's going to be a lot of discovery.
So another question for you, Zibi, and also for you, Morgan. So do we know if there is any magnetic field around Titan and then around Europa that is strong enough to block cosmic radiation or solar radiation, or the atmosphere in the case of Titan is enough for that?
Yeah, so for Titan, the atmosphere blocks the radiation, any of the radiation, and the radiation environment around Saturn isn't as extreme as the radiation environment at Jupiter. For Titan, the atmosphere blocks the cosmic ray environment, et cetera, to the point that for our gamma ray and neutron spectrometer, which is one of the other instruments on the lander, we actually have to bring a neutron generator because there isn't enough of a cosmic ray background to generate the species that we want to measure with that with the gamma ray and neutron spectrometer. So it's very protected actually compared to the surfaces of other of a lot of the other kind of exposed satellites, and that means that if there are the chemical materials, the compounds that we're going to measure can persist for long periods of time because there's not a lot breaking those down in terms of radiation impinging on the surface. Or were there, chemical biosignatures, those could persist for longer on the surface at Titan because it's so protected.
Thank you. I could have a SETI talk with you too, instead of having just a SETI live. But one more question I have here. Yeah, we talk about temperature. You mentioned that the temperature Zibi on Titan is 94 Kelvin, which is minus 290 Fahrenheit. I know, a Frenchman talking in Fahrenheit. That's frightening. But
we don't even do that. As scientists, we don't talk Fahrenheit. It's Celsius or Kelvin.
So it's minus 180 Celsius for the rest of the world, which is using Celsius units. So this is very cold. Like, I mean, the lowest temperature on Earth's surface is minus 60 degrees Celsius. So we are talking about worlds which are extremely cold. So someone asked the temperature on the ocean of Europa. Do we have an idea of this? Because if you're looking for life, it's kind of important to know the type of, the environment of this life.
Yeah, well, we haven't gone, through that ice yet and stuck a thermometer down there yet, but, there are concepts for melt probes that could actually go down and reach the ocean. We know it's liquid, so it's got to be right at or above the freezing point of water at the lowest, right? Whenever you have salts that are in liquid, you do get something called freezing point depression, so you can have things slightly colder, but we think it's probably around 4 degrees C, at least at the top. Now, one thing that's very exciting is that Europa's ocean shouldn't even be there at all, right? This should be just this boring, frozen, dead ice ball, but it's not. And the reason for that, we think it's partly due to tidal flexing. As Europa goes around Jupiter, it sort of flexes like this, and that creates some heat. There could also be some radiogenic heating from elements decaying. Anyways, I'm trying to keep it short, Franck, sorry. But the point is, it's hot, and there could also be hydrothermal activity down at the seafloor. And here on Earth, where we find these hydrothermal vents, it's places where geothermal energy can mix and create these beautiful chimneys. We see diverse communities of life, right? Not just bacteria. We find tube worms and crabs and octopods and stuff like that. Did you know tube worms can live to be over 200 years old? I just learned that the other day. It just blew my mind. Anyways, but the point is they can exist off of this kind of energy. And so that's what we think life in an ocean like Europa might be able to live off of.
All right, thank you. So, Zibi, one question we had from one person here is that, so we sent on Titan already a lander, right? The Huygens lander. So that was the ESA component of the Cassini mission, one of the ESA components. Do we have sound of the surface of Titan? And are you planning to have something like this on Dragonfly so we can hear the wind, the heavy wind of Titan?
Yes, so the Huygens probe was designed primarily to measure make measurements of the atmosphere, but it did send us back data from the surface of Titan. A cool fact actually is that when the Huygens probe was designed, we didn't know if the surface at that landing place was going to be liquid or solid. So Huygens was designed to make measurements of either a solid surface or a liquid surface if it splashed down instead of landed, which I think is just amazing to have had to design those two options into the lander. But in part, thanks to the Huygens probe, we know what to expect on Titan when we get there with Dragonfly. We do intend to bring microphones. Dragonfly will have a microphone. We'll be able to listen to the environment, although Dragonfly will make its own noise, so we may mostly be listening to Dragonfly and the sounds of Dragonfly on Titan. Another instrument we'll have is a seismometer, so we'll also be able to listen for Titan quakes, which is really exciting to understand, how seismically active an ocean world might be. Nice.
Okay, I want to ask you a last question for both of you. So you were both working in remarkable missions. I mean, I envy you somehow, sometimes, I will say. I mean, it's great. Telescopes are great, but having a mission that's going to fly on Titan or explore Europa and maybe in the future even land on Europa, it's absolutely remarkable. So what's your life like? What's your personal life? Do you tell people what your real job is and what do you do on a daily basis? And what do you think you're gonna be doing in 5-10 years?
Well, one of the things that's kind of unique to planetary science or astronomy is that very often we do know what we're going to be doing in 5 to 10 years, right? So Europa Clipper launches in 2024. So 5 years from now, the Europa Clipper will be in cruise. 5 years from now for Dragonfly, we'll be building the final, the flight hardware and getting ready for launch. And so we really already have things on our calendars for 5 to 10 years from now, which is kind of it's kind of unusual, I guess. these things sound really far away actually in terms of time, but the time is just going to fly by because there's so much that we have to do in all of these, in all of this time. So, speaking for me, I spend most of my days right now during the pandemic on Zoom, going from meeting to meeting, because we're really, on Dragonfly, we're really in the thick of things. We're in our phase getting ready for our preliminary design review, which is in just under a year now. And so there's a lot of, design work, a lot of development, testing, of different components in Titan-like environments, for example. So things are going well, and we've got, we're just super busy trying to get, trying to take each of the steps to get to our preliminary design review, and then start, start taking the next steps after that. So, I think I answered the different components of the question, but if I missed something, let me know.
No, it's good. What about you, Morgan?
Oh gosh, well, some of the things that Zibi has been doing, I've been helping with when it comes to Dragonfly and with Europa Clipper, but also I still get the chance to go into the lab for about a day a week and be able to replicate Titan's surface in the laboratory with cryostages and dissolve a whole bunch of things in a mini Titan lake and see kind of what happens. So we're doing some experiments to help us better interpret the data that we'll be collecting. And also thinking about what the future missions may hold. A future Europa lander mission concept, we're working on development of that. We're even looking at things like robotic snakes that could get down into, say, the crevasses of Enceladus or potentially Europa too. So it's one of the fun things about working at a place like JPL and doing work for NASA is you get to dream big and then see a lot of them realized. And it's the coolest thing ever. I just couldn't imagine doing anything else.
Well, thank you. That was a very good conclusion, in fact, for this SETI Live. Thank you to both of you for joining us. We have more than 250 people watching us live, so a lot of people here interesting to hear about life on Titan and Europa. I know you're extremely busy, so I really appreciate you took the time to speak to us today. For all our viewers, just I will remind you, this is the SETI Live, as a product of the SETI Institute. We are a non-profit organization located in California. We are searching for life everywhere in the galaxy. We talk a lot about astrobiology, astronomy in general. So you can support us by following us on social media, on Twitter, Facebook, YouTube, everything. We are there. By the way, Morgan is also on Twitter and very active, so you can follow her too. And if you like what you see, if you want to support our mission, you can also make a small donation, $1, 1,000, 100 million, and we send a mission dollar. And just go to seti.org/donate or look in the website. You will find a link for that. But we truly appreciate your support no matter what. Share our videos, talk about our mission, and just stay active and watch what we do in astronomy and in astrobiology. So for instance, next week, we are going to start a special series for the World Space Week in celebrating women in space. In fact, we could have started today. And this is something the SETI Institute is doing with Unistellar and the Planetary Society to help girls discover all the wonders and of space and the universe. So next week, we are going to have a special SETI Live on Thursday at 3 p.m. We will have Jessie Christensen and Sophia Gat-Nasser, and they are going to talk about exoplanet, dark matter, and the fun of making discovery by studying space. So thank you very much, everybody. Thanks again, Zibi. Bye-bye.
Thank you. It was really fun to talk with everyone.
Thanks, everyone. Stay curious.